punya kedudukan dan orang tak lalu.
Sebab dia orang nak live. So,
Guys, those who are sitting over there, you can actually come forward a bit. Yeah, there's a lot of space, right? Okay, we are starting now. Very good morning to everyone. Welcome to School of Physics, University of Sains, Malaysia. So today we have our speaker here, Dr. Kevin Koay. So we want to thank Dr. Chong for inviting Dr. Kevin to USM to give us a talk. So Dr. Kevin Koay, from what I heard, he is actually a Penang guy. So he grew up in Penang, and he was a Chongling boy also, right? No. Penang Free School, sorry. And he did a PhD in Curtin University, and he was a postdoctoral researcher in University of Copenhagen. And recently and currently, he's a postdoctoral fellow in Academia Sinica, Institute of Astronomy and Astrophysics in Taiwan. So his research interests includes active galactic nuclei, time domain radio astronomy, and interstellar scintillation and scattering. So today I'll pass the time over to Dr. Kevin. Let us put our hands together and welcome him.
Hello? Yes. Okay, very good morning to all of you. First of all, I want to thank Dr. Chong, the organizers, and everyone here for giving me this opportunity to give a talk here in USM. Is it okay? Yeah, and as he said, I was born in Penang, and I actually spent 18 years living here, actually around the Changkat Minden Heights here. So USM has always been, I always pass it when we're going home or cycling around. And USM has always been a big part of my life growing up. And it's good to be back here to actually give a talk. Okay, so before I start talking about black holes and all this thing, maybe I'll just introduce myself a bit more. I actually graduated, I did my bachelor's degree here in Malaysia in Multimedia University. And my first work in research actually was not on black holes or whatever, but it's actually rice fields. Okay, I hear there's actually a big remote sensing group here as well. And my master's thesis was actually working on remote sensing of rice fields, okay, with radar, satellites. Okay, and then when I was doing my PhD, I decided to do something that I'm really passionate about, do astronomy. The thing that was closest to me was, of course, radio astronomy. So I thought, I'd switch to radio astronomy. And I did my PhD on, before that I was doing scattering of radio waves on rice fields, right? So decided to work on scattering in the interstellar and intergalactic medium of waves coming from space. I think it's like fast radio bursts. I think some of you may have heard of it. Also from supermassive black holes, or what we call active galactic nuclei. These are in the centers of galaxies, and they are really bright. You can see them from billions of light years away. And when I was in nuclei, okay, which is all this stuff falling into black holes, and they produce a lot of heat, a lot of light. And actually, most of them outshine the stars in the whole galaxy. Okay, and I was studying how, these black holes were fueled, or how they accrete gas, and also how they produce these jets, which can get launched out at speeds close to the speed of light, and they travel for up to hundreds of thousands of light years. Okay. And this was what I was doing mostly, and I used ARMA and a very large array, mostly radio telescopes to do my work. I'm an observational astronomer, which is why this talk that I'm going to give, okay, on the Event Horizon Telescope, I'm going to give it as an observer, okay? So there are people people like Stephen Hawking and Kip Thorne, they are very smart people. They do theoretical stuff, general relativity and all these things. But for me, I'm not so smart, so we all do observing easier, I think. Okay, so I'll give an observer's perspective on the Event Horizon Telescope. And this is a project that I've been working on in the last 2 years since I joined Academia Sinica. Okay, just a bit more introduction. I think Chin Fei was here last year, right? And he introduced ASIAA. He showed a nice picture of the lake next to our building. Okay, so what ASIAA does is it's quite people who do all kinds of physics, from planetary science, belt objects, to people who study dust in the interstellar medium, star formation, and in the star formation group of people. There are people also who do cosmology, extragalactic astronomy, high energy astrophysics, and actually one of the big strengths of ASIAA is actually in instrumentation. So about there are about 200 staff there, and about half of them are actually engineers, technicians, and all this, and they are involved in, for example, we work with Harvard Smithsonian to build the sub-millimeter array on Mauna Kea, and JCMT also, as part of the East Asian Observatory, ASIAA also has a share in it. And of course, now we're using the Greenland Telescope, and this is the project that I'm involved in ASIAA. And ASIAA is also one of the big partners in ALMA. In fact, Chin Fei is leading the group to develop some of the software for ALMA. And ASIAA now in Taiwan, they are actually building the band 1 receivers, which is about 80 gigahertz receivers for the whole ALMA array. Is being built in ASIAA now. And also for optical telescopes, ASIAA is involved in this Japanese one, Subaru. And we also have nanosims to study meteorites and things like that. Okay, so yeah, ASIAA, their strategy has been to partner with, I think Dr. Chong was saying this morning, their strategy is always to partner with the big institutions in the US and all over the world and contribute funds and expertise in terms of the technological side now. Okay, so going back to black holes, I think in the past, we need to introduce more about black holes and all these things, but nowadays we see black holes so much, right? Especially in movies and all that. How many of you here watch Interstellar? Only the younger people. Okay, I mean, black holes are very ubiquitous now in the media. You hear about it all the time. And of course, recently you heard about those. Did you read about the discovery of the gravitational waves? Ago, where they detected gravitational waves from 2 black holes. Okay, these are stellar mass black holes. These are black holes which were formed after stars explode, and then gravity causes all the matter to collapse onto themselves, and they form black holes. Okay, and they saw 2 of them merging together, which produce gravitational waves, right? And these are usually about 5 to 100 times the mass of our sun. Okay, this symbol here, we call it the solar mass. So basically, these stellar mass black holes, they have that kind of mass. Okay, on a slightly higher range, we have what we call intermediate mass black holes, and we think they exist in the center of perhaps globular clusters. Okay, so which are groups of stars. And some people claim to have discovered intermediate mass black holes, but this is still a very controversial topic. People are still questioning whether these are real or not, okay? But of course, some of the most well-known black holes are the ones that we see in the centers of galaxies, okay? We think that most, if not all, of the large galaxies we see, in the center there will be a supermassive black hole, okay, of mass about 1 million to about 10 billion the mass of our sun. Okay, in fact, the center of our own Milky Way galaxy, okay, we know there's a black hole there, about 4 million times the mass of the sun, okay? And we can actually observe stars going around, okay, orbiting this object. Okay, they've been monitoring these stars for about 20 or plus years, and they can measure the mass of this object. It's about 4 million times the mass of our sun, and it's totally dark, okay? It doesn't emit any light at all at optical wavelengths, okay? But in radio you can see it's really bright. Okay, so there's already a lot of kind of evidence, okay, that black holes exist. All right, but of course the holy grail, okay, is actually to capture an image of a black hole. Okay, nobody has actually seen a black hole directly. Okay, we only can measure it based on stuff that's going around or orbiting it. Okay, and like I said, this is one of the remaining grails in physics today, to capture the image of a black hole. Of course, can we actually see a black hole? No, right? I mean, that's a paradox, right? A black hole is supposed to be an object where gravity is so strong or space-time is curved around it, such that light, even light, you travel at the speed of light, you cannot escape it. Okay? So how do you see a black hole? Okay, the thing is, there's a lot of stuff, okay, a lot of matter, gas, stars, whatever, that's actually falling into the black hole. Okay, maybe gas or dust or whatever. Okay, and these things, as they fall in, they lose a lot of energy, right? Because of gravity. And then this energy is released as heat and radiation. Okay, and that's why it's very hot. Okay, and this is what we call the accretion disk, which is the stuff that is going in, falling into the black hole. Okay, of course, this picture is from the movie Interstellar, those of you who watch. Okay, and what is this ring here? Okay, this ring here is what we call the photon ring. Okay, this is actually, so the accretion disk is going this way, it's falling into the black hole. But the stuff that is behind the black hole, what happens? Because of, general relativity, it gets bent, okay, because space-time is warped around the black hole. The stuff that is behind the black hole actually sort of gets, the light from behind sort of bends and travels to the observer, okay? So what we're seeing, this ring here, is actually from stuff, the part of the accretion disk that is behind the black hole. Okay, so technically, while we cannot observe or see the black hole or the event horizon, okay, we can see the stuff that is going around, falling into the black hole, and from there we can see what we call this, the shadow of the black hole. So we say this is the silhouette of the black hole itself. And this is the image that we want to capture, okay? So like I said, we cannot actually see the event horizon of the black hole. Okay, so if this is the event horizon, okay, there is, imagine all the light that's passing through near the black hole, okay, from elsewhere in the universe. Okay, and most of this light will sort of just get bent around due to general relativity. Okay, because of the curvature of space-time, they'll get bent around and travel around the black hole. But there will be certain paths where any light will fall, and it fall eventually into the black hole itself. Okay, and light that goes through this path, they cannot escape. Okay, and here this will be dark. Okay, this region, if you observe the black hole from here, this region will be dark, and this region will be bright. Okay, and this is for a non-spinning black hole. So based on the theory people, okay, the smart people, they tell us that this shadow, the size of this shadow, will be about 5 times bigger than the Schwarzschild radius. Okay, what is the Schwarzschild radius? That is the event horizon. Okay, that is the radius around the black hole where anything that falls in will never be able to escape. Okay, and the size of this shadow for a black hole that is not spinning will be 5 times the Schwarzschild radius. Okay, and what is the size of the Schwarzschild radius? Okay, the Schwarzschild radius is very simple. It's given by 2 times the gravitational constant times the mass of the black hole divided by the speed of light squared, okay? And these are all constants, okay? The only value that is changing is the mass. So if you know the mass of the black hole, you know the size of the event horizon, then you know the size of the shadow. Very simple. Black holes are very simple objects, right? Okay, now this is for a black hole that is not spinning. Okay, for a black hole that is spinning, what happens? Okay, the space-time around the black hole gets dragged along as it spins, okay? So now things get a bit more complicated, but the size of the shadow is still the same. It's still about 5 times the Schwarzschild radius, okay? But there's a slight difference, okay? You see more light coming around one side. Okay, so one side of the photon ring will be brighter than the other side, okay? Or thicker and brighter than the other side, okay? So if you can capture an image of a black hole or the shadow of the black hole, okay, you can actually tell whether the black hole is spinning or not, okay? I can measure the spin. And here is a sort of animation, some Hotaka from Harvard who did this, showing what we think it will look like, okay? And this is stuff that is falling into the black hole, okay, from the front, so part of it is covering the black hole. But the stuff that is behind gets warped and bent around the black hole in this, what we call the photon ring, okay? And you can see one side of the photon ring is brighter than the other because the black hole is spinning, okay? And of course, the theories have all kinds of models because we haven't seen anything yet, right? I mean, so they can make all kinds of models and have all kinds of predictions, put all kinds of physics into it, okay? So once we have the image, we can compare with all these models, and some of them, most of them, I don't even know what it is, except maybe radiatively inefficient accretion flow. Okay, there's a lot of theories about how all the matter actually falls into the black hole. And based on the different theories, we'll see different things based on the image we get. Okay. Now, if you want to capture a black hole shadow image, okay, you need to find the right targets, okay? So what are the biggest black holes that we can see from Earth, okay? Of course, some of the biggest ones we measured, like the masses. They have masses of tens of billions of, tens of billion times the mass of our sun. Some of them are very far away, 10 billion light years away, 20 billion, 12, 13 billion light years away. They are too far away. We can't resolve it from the Earth, okay? So the black hole that is the largest in size, in angular size, okay, as seen from the Earth, is actually the black hole in the center of our galaxy, okay? And we call it Sagittarius A star because it's actually towards the direction of the constellation of Sagittarius, okay? This image was taken by the new radio telescope in South Africa, which is one of the SgrA sort of telescopes. And this is at, I think, about 1 gigahertz, I think. And you can see in the center it's very bright in radio. Of this, we know there is a big black hole. Okay, 4 million times the mass of our sun. And like I said, 4 million times the mass of our sun. From the mass, we can actually calculate the size of the shadow, okay? And the size of the shadow, we expect it to be about 50 micro arc seconds. Okay, how big is that? Okay, how many of you have your own telescopes at home? You have, right? So what is the angular resolution of the telescope? A few arc minutes, right? Hubble Space Telescope, the angular resolution is about 0.1 arc seconds, right? So this is 50 micro arc seconds, okay? 1 micro arc second is about a millionth of an arc second. So the resolution is very, very small. You need to be able to see the black hole, okay? It's like trying to observe, maybe you saw a coin, found some of the astronauts drop a coin on the moon. You want to see whether it's worth building a spaceship there to pick up the coin or not. You want to see what value of money the coin is, okay? So you need to actually be able to resolve, okay, the coin to see how much is it on the moon. And that is the kind of angular resolution you need to see the black hole shadow, okay? So can we do this, okay? So that's what we're trying to do. Now, that is our primary Event Horizon Telescope, okay? The next target, the next biggest black hole that we can see from the Earth, okay? So these have to be supermassive black holes. The small stellar mass black holes, we can't see them at all from the Earth, okay? The next target is the black hole in the center of this galaxy called M87, which is an elliptical galaxy, all right? It's much further away. It's 54 million light years away, okay? But the black hole is much bigger, 3 to 6 billion times the mass of our sun, okay? I mean, it's more massive, okay? And we expect the size of the shadow to be 20 to 50 seconds, okay? Because this is more distant, we can't measure the mass as accurately as a star. So there are actually two different mass measurements, okay? Some say it's 3 billion light years, some say, 3 billion solar masses, some people say it's 6 billion solar masses. Depending on which one, okay, the size of the black hole will be 20 to 40 micro arc seconds, okay? And this source is very different. The one in the center of the galaxy is actually quite dormant. It's not doing much stuff. There's not much stuff falling in, okay? But M87 actually is accreting. Well, there's a lot of stuff that's falling in. And the black hole, somewhere outside the black hole, either from the accretion disk or somewhere, is actually producing a jet, okay? So this is something we see in many, many supermassive black holes, and also some of the stellar mass black holes we see. Okay, as matter is falling into the black hole, accreting, okay, some of this stuff gets ejected, okay, out. As magnetic fields and winds and all this, they produce these jets. Some, like I said, they travel relativistically, okay, some of them a few, okay, almost close to the speed of light, okay? And some of them get ejected very, very far away, up to 100,000 light years away, outside the galaxy. And they actually mess up, So this is the jet in M87. The jets actually sort of mess up what we call the intergalactic and interstellar medium in the galaxy itself. Actually, they can actually cause stars to stop forming in the whole galaxy, okay? And this region here in red here, okay, if you zoom in with radio telescopes, interferometers, you see this jet, and you can zoom in more and more and get very close to the black hole, okay? So some of the latest ones, this was done by Kazuyo Hada, one of our colleagues. You can actually reach very close to the black hole, okay? This is just to show what you expect the size to be, okay? So we're already very close, okay, with interferometry. And what is it we want to answer? Okay, of course, capturing the image of the shadow of a black hole in itself is a very wonderful achievement. You can see it, but what do we actually want to learn, okay? Number one, we can confirm that there really is such a thing as an event horizon. There really is a black hole and not some other thing that is there, okay? And of course, we want to test how well Einstein's theory of general relativity still holds close to a black hole. We want to find out how matter actually accretes onto a black hole. Okay, and all the different theories we have, which one is the right one? Okay, and do black holes have spin? And you can see that from the image, right? One side will be brighter and thicker than the other side if the black hole is spinning. Okay, and how are black hole jets launched? Okay, so many of these black holes we see, they have these huge jets, but nobody really knows how these jets are produced and launched. Okay, for like MA7, this huge jet, I mean, for all you know, okay, we don't know what's happening down there, what is launching this jet. Colleagues tell me that this Ultraman, this thing is actually called the M87 beam. Okay, it's named after M87. Okay? And this was, well, how many years ago? 1970s. Jim Bardeen was a physicist. He said it's conceptually very interesting, okay, if not astrophysically very important, to calculate the precise apparent shape of the. You can learn from it. Unfortunately, there seems to be no hope of observing this effect. This was these. Okay, but now we believe we can do it, right? So we have this Event Horizon Telescope, which is, the goal is just to combine all the millimeter, 230 gigahertz telescopes all over the world, okay, to form a giant radio telescope, okay? So, how do you increase the angular resolution of a telescope? How do you get a higher resolution for a telescope? You increase the diameter. Okay, the bigger the telescope, the higher the resolution, right? So, the very biggest telescope that you can build on the Earth is the telescope the size of the Earth, okay? Of course, you can't build it physically, but what you can do is using interferometry to combine all these telescopes to function as a telescope as big as the Earth, okay? And we call this the Event Horizon Telescope. And they work at 230 gigahertz, because the higher the frequency you go, okay, the smaller the telescope you need, okay? It's always relative to the frequency. Okay, so we have, in the Event Horizon Telescope, we have ALMA, which I think many of you know, is one of the biggest interferometers we have now in Chile. We have the James Clerk Maxwell Telescope and the SMA, both of which ASIAA has a big share in it. And then we also have the large millimeter telescope in Mexico, the sub-millimeter telescope in Arizona, Pico Veleta. This is Iram in Europe on a mountain. Okay, and we have a telescope in the South Pole as well, South Pole Telescope. And later I'll talk more about the Greenland Telescope. Okay. So this EHT Event Horizon Telescope is a kind of a global collaboration. We have partners from the US, Chile, Europe, and East Asia. And it's funded by a lot of institutions, including ASIAA, and also the Ministry of Science in Taiwan. Institutions, these are the main institutes that are participating in the EHT. Okay, Academia Sinica is one of them. Okay, and these are institutions who are the main contributors, and they actually contribute telescopes to the EHT, okay, instruments. And then on top of that, you have all the affiliate institutions, which are, we have scientists sort of working on the project itself, okay? Now, how does the EHT work? So how much more time do I? Okay, so how does the EHT work? This is based on radio interferometry, okay? So how many of you are familiar with this? Interferometry. So basically how it works is you have two antennas separated far apart. You observe this wave that is coming in from space, okay? And what the interferometer needs to do is to combine the signals in the correlator. Actually what you're measuring is how correlated the signal is, okay? But of course, the time it takes for the wave to reach this antenna and this antenna is different, okay? There is a small time delay, which you need to introduce and model into your telescope, okay? Here. You have to compensate for this time delay, okay? And these are what we call, like, for example, the Very Large Array and ALMA. These are what we call connected element interferometers. They are located in the same location. They're all connected by fiber optics, so all the data sort of gets connected and sent to the correlator immediately, which is at the site, okay? But for EHT, it's different. It works on this principle I call very long baseline interferometry, where the telescopes are actually on different continents, right? Which presents a much bigger challenge, okay? number one, that you cannot send it all through internet to correlate it immediately because the data sizes are huge, okay? So what you need to do is record all the information in disks. Okay? Last time they used magnetic tapes, okay? And there's a lot of storage needed, okay? Now because all of them are recorded, and remember, you need to put different time delays in different telescopes because the wave arrives at each telescope at different times, right? So you actually need to record the timing very accurately. So all of these telescopes at their sites, they all have atomic clocks. Okay, mostly we use hydrogen masers. Okay? But there's a bigger problem, okay? The Earth is rotating, right? It's also precessing, right? When all your telescopes are on the same site, it doesn't matter that much. But when your telescopes are separated far apart, one telescope maybe may be moving towards because of the rotation. Okay, what happens? The time delays is changing all the time. The time delay, okay, when the wave arrives, is changing. And you have to do that. We have to model actually the rotation of the Earth, the precession and all these things, and put it into our calculations of the time delay. Okay? Not only that, however well you want to model it, there is always some inaccuracy. Okay, sometimes there's some big earthquake or whatever, it will also affect the Earth. Okay? So to do that, we need to calibrate it. Okay? Calibrate during the processing. And then there is the Doppler shift effect. Okay, like I said, your Earth is rotating. If you're looking at the source there, this telescope is this side, this telescope is this side. One telescope maybe is moving towards the source. One telescope is moving away. Because of a Doppler effect, you can be measuring slightly different frequencies. And it's changing as well with time. So you need to correct for this in your model as well. Okay? And when your telescopes are together, the atmosphere is similar, right? When you look up at the sky. Now your telescopes are in different countries, different continents. The atmosphere is different. There'll be differences in the time delay as the waves pass through the atmosphere as well. We have to calibrate all these things when we do VLBI. Okay? Now, VLBI has been done for more than that, 40, 50 years. Okay, at radio, sort of 5 gigahertz up to 20. That's now it's very easy to do. Okay, we have been doing it for a long time. But 230 gigahertz, is very new. Okay, and it presents a different kind of challenges. Okay. Oops. Number one, 230 gigahertz, although it's very good for observing black holes. Okay, because of course we want the high resolution. And also because the accretion disk, we think, emits at around this kind of frequency, okay? But 230 gigahertz, part of it is absorbed by water, okay? So the atmosphere, actually, water in the atmosphere, okay, water vapor, absorbs light at 230 gigahertz. So all the telescopes that we need, okay, most of them who observe at these frequencies, they have to be built at very high locations where you are, clear of a big chunk of the atmosphere. Or places that are very dry, for example, like Alma is one of the driest sites on Earth, okay? The South Pole is very dry because most of the water is locked in the ice, okay? Same with the Greenland Telescope. And no matter how good your site is, you also need to be lucky also because even if the sites are cloudy or whatever, then too bad, a lot of these will get absorbed. Okay, so this one, we still have to be lucky and hope for good weather, okay? And not just good weather at your telescope site. Remember, you have telescopes on different continents. You actually have to have good weather at all the sites at the same time, which is a challenge, okay? And at this frequency, these high frequencies, the atmosphere changes very quickly. So you cannot, okay, if you want to observe a faint object, if you want to take a photograph, okay? A faint object, you just increase your exposure time, correct or not? Okay, but we cannot increase our exposure time indefinitely, because the atmospheric phase changes occur at about 10 seconds. So you can only increase your exposure maximum 10 seconds. And because of that, we are actually very limited to observe only the brightest objects. Okay? And thankfully, some of these black holes, the accretion disks, they are very bright. Okay? But of course, now we have ALMA, which is very, very sensitive telescope. When you combine it, the sensitivity of ALMA actually increases the sensitivity of the whole telescope. Okay? Now, the other one thing I would say is, for event horizon telescope, the UV coverage is not optimal. Okay, what I mean by UV coverage, okay, I'll explain in the next few slides. Okay, still got time. Okay. An interferometer doesn't measure or capture an image directly. Okay? Now this is a picture of image of a cat. When you say an image, what you're measuring with your optical telescopes or your photograph, your CCD, you take a picture. You're measuring the brightness distribution on the sky. Okay? But what you're measuring with an interferometer is actually the Fourier transform of the image. Okay, so this is the Fourier transform of a cat. Okay, but don't worry, no animals were harmed when doing this presentation. Okay, and this is what an interferometer actually measures. Okay, the flux density. Okay, or how correlated the signal is between two antennas. Okay, I'll give you an example here. So this is a very large. Okay, and you're measuring how correlated the signal is from two antennas. Okay, and the shorter spacings, the short baselines we call it, the antennas that are situated close together, they measure the large scale. Okay, they measure large scales in the image. Okay, but the information you get from two widely separated telescopes, okay, maybe the larger baselines, they measure the small scale objects, the small scale structures. Okay, and so we go back to the cat, and this is in Fourier space. If let's say I draw a square here, okay, and I take out all the information from, let's say the middle here. Let's take out all the information from outside. Okay, so the ones outside here are measured by the long baselines. Okay, and I take out all the information and I just keep the information in the middle here. Okay, what will you see? Okay, all this information has been taken out. You just keep the information short spacings. Okay, you can see the resolution is much lower now. Okay, you only see the large scale object, the large scale stuff. In fact, here, sorry if it's not clear, you can actually see the whiskers on the cat, but here the whiskers are totally gone. You don't have the resolution to get the whiskers. Okay. Now, what if I do the other thing? I keep all the information outside. I remove all the information in the middle here, which is to remove all the information from the short baselines. Okay. You see this. What you detect is only what you detect is only the sharp features. Okay, you can actually see the whiskers here, or the very sharp features, but all the extended large-scale structures are removed from the image. And when you do VLBI, most of the time this is what you see, because the telescopes are mostly far apart on different continents. Okay, so you're losing a lot of information on the large-scale structure, but you have very high angular resolution. Okay. Now, the problem also with the Event Horizon Telescope is even in VLBI, you can arrange your telescopes, you can still get, mix and balance, structures across from short to, large scale. Okay, but the EHT, like I say, is very limited on where you can build the telescopes because of the atmosphere. It has to be on mountains or very dry sites. So the UV coverage, okay, this is what we call the UV coverage, the information, okay, how much information you get from the Fourier space. Okay. So the UV coverage from the EHT is quite poor. Okay, here you're collecting information from all over in this space, but here you see the information you're collecting is just in these regions. So you have to fill in the missing information. Okay, but what we can do, okay, these people, they are very smart, okay, the astronomers. I mean, because the Earth is rotating, right? You can actually use the rotation of the Earth, to actually, as it rotates, you actually have slightly different baselines, okay? Because the telescope, if you are observing, let's say I'm the source, okay? I'm looking at all the telescopes on the Earth. As the Earth rotates, the baselines actually are changing with respect to me as the source, okay? So this is using the rotation of the Earth to actually fill in information, okay, on the Fourier space, okay? But even that, there's a lot of missing information, but you can use a lot of assumptions and whatever to fill in the space, and then you Fourier transform it to get back the final image. Okay, so in April 2017, okay, we had our first EHT campaign together with all these telescopes. We observed Sagittarius A star, M87, and about 10, 15 other people all over the world, in Chile, South Pole. I was in Hawaii in the James Clerk Maxwell Telescope. And this was a very interesting experience because this was my first time being at high altitude. My boss asked me before I go, have you been to high altitude work before? I said, the highest I've been to is, I was thinking, okay, Genting Highlands. I go and check how high is Genting Highlands. Okay, 1,800 meters. This one is 4,000 meters. The oxygen level is different, okay? Some people, they get headache. But thankfully, when I went there, no headache. But you can only go to the telescope, you know, the maximum is 13, 14 hours you can stay there because of oxygen. And you actually stay halfway up the mountain, okay? So, you know, there was a big thing because, like I said, weather is the biggest, you know, you can prepare. We actually did rehearsals and everything. But on that time, if your weather is bad, then you can't do anything. So 10 days observing indoor, but we had total 5 days of observation. So every day we'll wait. Command center in MIT, they are the ones who will check all the weather and all the sites. Okay, go. Okay, every day they'll say go or no go. Okay, and we have all the schedules ready to observe all different sources. And you are there, you know, like sometimes 10, 15 hours near the end. Because your brain doesn't have enough oxygen. You're like, you're not even thinking properly. You know, you point here at different telescopes. You have to make sure you schedule every 5 minutes, point which source. So that's kind of a challenge, okay? Of course, the people in the sub-millimeter array, they're lucky because their control room, they pump oxygen inside, but for us, we didn't have. Okay, JCMT is an older telescope. Okay, but 2017, we actually had perfect weather at all the sites. Okay, if you look at our pictures, look at the sky. Okay, here, perfect, Hawaii, everything. We had perfect weather at all the sites for the first 3 days. Okay, and we actually got very good observations out of it. Okay, so my colleague was saying, you know, this is proof that God exists and he wants us to see the black hole. Okay, and not only the EHT telescopes, okay, because everybody is excited, right? Also observing at the same time, okay, some of the gamma ray telescopes, X-ray, these are space telescopes, and optical, very large telescope, okay, and also some of the lower frequency radio, they're all observing at about the same time during our campaign in 2017, okay? And this is for, previous one was for Sagittarius A star, and this one is for M87. Again, all the observations were scheduled at about the same time so we can learn, you know, as much as we can. This is what I call a multi-wavelength campaign. Okay? So what happened? After that, all the data was sent. So they observed at sort of 2 bands simultaneously. The high frequency band was sent to Planck Institute in Germany, and this was there. The other half of the data was sent to MIT to do the correlation, okay? And so this is just half the data. Okay, guess how much data there is here? Yeah, it's petabyte level, okay? Yeah, and of course, in the South Pole, there are no flights to the South Pole during winter, right? So even though it's in April, until October, before they could fly the disks out from the South Pole. So I said, no flights, okay, you have to wait. And what was done? They correlated all the data, petabytes of data, and for the last year, mostly 2018, but from end of 2017, what I've been doing also is actually to help to calibrate all the data, okay? Remember I said there's a lot of calibration you need to do, right, to correct for the atmosphere and all these things, the delays and all these things, so we've been calibrating. So once you correlate, you move from petabyte to terabyte level, so we are doing all the correlation, the calibration with terabytes of data. Some of it was done in ASIAA, okay? And after that, since August 2017, we actually made the first images, okay? And because this is a potentially very groundbreaking kind of science, we have to be very careful. So we're calibrating the data. We actually use 3 different softwares to calibrate. We use some of the typical ones we've used in VLBI for a long time, but we also develop our own software for calibration after we compare results, see whether the delays that we are getting from different ones are the same, whether it's consistent, okay? And we made the images, okay? There was about 30 of us, okay? Each of us was supposed to make the image on our own, okay? Then we do the Fourier transform and have our own assumptions and everything, okay? And the rule was that we were not allowed to communicate with each other. Okay, we all make our images independently. We use what we think is the best method or, you know, the best assumptions or whatever. After that, only we all came together, okay, to actually show our images and compare our images. And that was during an imaging workshop we had here. And that was the time when I was back here. Okay, because I told you my father-in-law's 80th birthday, so I couldn't miss that, even though this was so exciting, right? But they let us do it by telecon. So because this was in the US, when I was back here for holiday, every night from 9 p.m. to 5 a.m., I was on the telecon and discussing with all these things, sharing our images. Of course, I can't miss my father-in-law's birthday, but I don't want to miss this also, right? We're comparing all our images for the first time, okay? And in November 2018, just a few months ago, we all were in Radboud University in Nijmegen to discuss our results, analyze everything. You can find on Facebook. I think the Event Horizon Telescope, they share on their Facebook page. Okay, we are discussing our results, discussing about publications and things like that, okay? Now, unfortunately, that's all I can say, okay? Because currently all the results, everything is under embargo, okay? But what I can say is that, okay, this is a simulated image. If the thing looks like this, okay, we know that the EHT in 2017, okay, actually has the resolution. If there's a black hole, we would have seen it, okay? Okay, this is contour, this is not a real one. So, because if I show anything, I'll get kicked out of the collaboration, okay? So, someone was joking at that time we were having a conference that, should we limit all the EHT members' collaboration to, because in other, in other countries, they give colloquium, I like to go and drink and all this. So should we limit the alcohol of EHT members until the first results are published? But, I mean, I was just joking. Okay, but stay tuned for the first results. I think it should soon. Okay? Within the first half of 2019, should have the press release and everything. Unfortunately, I can't show it here, okay? So, let's see how much time. Okay, so yeah, a few more minutes. I want to talk about something that we at ASIAA are also working on, okay? So ASIAA, as part of the EHT collaboration, we've also been involved with the EHT in terms of picking a new site for the telescope since the early 2000s, okay? Now, so they were searching for this site. So this was way before I joined ASIAA, okay? So they've been looking for a new site to improve the UV coverage. Remember I said the more telescopes you have, the more information you collect, the more UV coverage field, the better and more nicer your image will be. Okay? So they've been searching for a new site, and this is a map showing the water vapor in the atmosphere, okay, on 2 different times. Okay? It's in February, which means it's winter in the north, but summer in the south. It's winter in the south, summer in the north. Okay? Now, in the southern hemisphere, there's actually, so the red color means very bad, a lot of water vapor in the atmosphere. Okay, the precipitable water vapor is more than 3 millimeters. Okay, ideally, during, like for ALMA and all these, the sites we want about 0.1. Okay, 0.1 millimeter, right? Okay, so these red sites are all out. The good sites, okay, in the south, you can see there's not many good sites, okay, except the one where ALMA is already there, so there's no point building another telescope there. Okay, and also Antarctica, where there's already another telescope. Okay, so in the north, they found one place in Alaska, but that place is very difficult to access. Okay, there's no infrastructure at all. Yep. So we also found Tibet, okay, which is a nice site, but because it's actually on the total opposite side of the Earth, you cannot form a baseline, you cannot observe together with ALMA, so there's no point building there. Okay, so the best place is Greenland. Okay, you can see even in summer, you can see some blue part here, which is very good. Okay, not much water vapor in the atmosphere. Even in summer, okay, winter, of course, is really good. Okay, and it's on the same side as ALMA, so you can observe together with ALMA. Right? And the conditions are actually very similar to the South Pole and also the ALMA sites. Okay, with the Greenland Telescope, you see you can improve. These are the red ones, the red lines here. You can improve the UV coverage, okay, especially in the north-south direction. Okay, you can form baselines with all ALMA and all these things. But the problem with Greenland is it's in the north, whereas the center of our galaxy is in the south. Okay, so you cannot observe Sagittarius A star, but the main target will be M87. Okay, and on top of that, they'll observe all the other sources as well. Okay, and of course, this is Greenland Telescope now. ASIAA, we are actually working together with Harvard-Smithsonian in the US, okay? And these are all the other telescopes that ASIAA is involved in, so we can have access to all this. Okay, so the Greenland Telescope actually started as one of the ALMA prototype antennas, okay? So before they built ALMA, the North American, the European side, they built their prototypes, okay? The European one is now in Chile, okay? It's nearby ALMA, they call it APEX, okay? Actually used for telescope, for real observations, okay? Now the North American prototype has been sitting at the VLA site in New Mexico since 2006, and nobody was touching it. Okay, so it was awarded to ASIAA and Smithsonian Astrophysical Observatory, okay, in Harvard. And this telescope was sort of awarded to them, and now they can do whatever they want with it. Okay, so 2012, they went and checked, see everything is working because it was just sitting there, and everything was still working, okay? And then what they did, they disassembled everything, and because this telescope was not built to withstand, minus 60 degrees Celsius, which you need in the Arctic, right? So they had to retrofit everything. So everything had to dismantle and rebuild again the parts which they feel that you need to withstand the minus 40, minus 60 degrees temperatures in the Arctic. So they retrofitted it. Okay, 2016, in March, they shipped everything to Virginia. They built everything up again to test to see everything is working, okay? Then they shipped it all the way to Greenland. So this is in Japanese, this is my boss's. Okay, shipped it all the way to Thule, okay, which is a US Air Force base in Greenland. Okay, the Air Force base is to stop nuclear missiles from Russia. Okay, of course now it's still an Air Force base. Okay, so everything was constructed in Thule, built the dish up, and reassemble. Okay, so the base or that thing, the stand, they built it on the side straight away. But for the dish, because this one they need a lot of finger work, the engineers need finger work, and it's very hard to do it with gloves. So they actually built this whole dish inside one of the hangars, okay, the aircraft hangars, and then they moved it after that to the site and put it up on the telescope. And then by 2017, okay, everything was done, completed. Okay, the engineers did a great job. Okay, and at the same time, okay, all the electronics, all the receivers and everything back then was actually built in Taiwan. Okay, the receivers, everything. And then before shipping it to Greenland, they actually shipped all the receivers and electronics all to Hawaii first. Moved it up to the James Clerk Maxwell Telescope and put everything there, test to see everything is working or not. Okay, so everything was working, and then they shipped it all the way to Greenland. Okay, and once they put it in telescope, that's when the scientists go in, okay, to do all the final parts of the scientific commissioning. And when the receivers were installed, I think it was like August or September. Okay, after the scientists started doing the commissioning, and we actually got our first light. Okay, this is a very big milestone when you're building a telescope. That means once you put everything in, okay, to test everything, our system is working, point at some astronomical source. Okay, and the first detection, we call it the first light. Okay, and we have our first light on Christmas Day, December 2017. Okay, so everybody was at home enjoying Christmas. Okay, me and my boss were there, two lonely people, and we observed the moon for the first time. Okay, and of course it's winter. So Venus, planets, everything was below the horizon. So we only had the easiest target to observe. Okay, of course there's no sun at all. It's 24-hour darkness, right? And we were out there, minus 30 degrees Celsius, taking picture of ourselves with the moon and the telescope. Okay, so this is an azimuth scan of the moon, and you can see here it's darker, okay, because, yeah, and here is slightly brighter. Okay, this was at about 94 gigahertz, okay? Just about 2 weeks later, okay, we detected our first spectrum, okay, which the spectrometer was working. Okay, with this we were pointing at our Orion. Okay, and this is carbon monoxide, okay, the emission line from Orion, okay, the Orion Nebula. Okay, and of course we took a picture. So on the telescope there's actually an optical camera, so a small one, okay? So we took a picture of it. Okay, and we had our first spectrometer. in January, okay, we were all rushing for this deadline. This was the EHT Event Horizon Telescope dress rehearsal, okay, to check everything is working. Okay, we observed one of the bright quasars, okay, supermassive black hole, 3C279. Okay, and we were joined by ALMA and the South Pole Telescope. Okay, and this was the longest VLBI observation from north-south, okay, in the history of VLBI, in the history of astronomy. Okay, we observed, in the Arctic, also South Pole, okay, at the same time, the longest, okay. And this time I wasn't there, I was back in Taiwan. And we actually did have the first detection, first fringe, okay, with ALMA. So we say we want to combine the signals together to do VLBI, right? Detect the signal between ALMA and our Greenland Telescope, okay? And in 2018, April, the Greenland Telescope actually joined the Event Horizon Telescope observations. Okay, and those data are still being processed. Like I said, now we're still focusing on the 2017 observations, and there's so much work to be done. Hopefully after this, we'll move on to the 2018 observations. And once that was done, okay, we started testing the 45 gigahertz receiver, and I was there also at the time. We also had our first light for the 345 gigahertz, okay? And we also joined some test observations with the Event Horizon Telescope at 345 gigahertz. Okay, 345 gigahertz, so far nobody has done any VLBI before. This is actually the highest frequency ever for the history of VLBI. Okay, again, we detected the moon. We haven't got any detection. It's actually still in Greenland. Haven't shipped to MIT for the correlation yet. So hopefully we detected something with ALMA. Okay, and this was in September this year. Okay, and actually during the time I was there, we actually had a very nice, we had a visitor. Neil deGrasse Tyson actually came and visited us with a National Geographic film crew to film the documentary. So of course we all fanboys, so we all happy with him. Okay, but he's a very nice guy. I mean, he talks a lot also. I mean, he actually gave a talk at the US base. So currently we are actually staying on the US Air Force base when we're there. Okay, but it's actually a very nice place. I've got gym, got movie theater, everything. Okay, now the current site in the Air Force base is actually just temporary site, or we hope it's temporary. The original intention actually is to move the telescope to Summit Station. Okay, even now at sea level, we are already making very good observations. Well, atmosphere is very good. But Summit Station, 3,000 meters, okay, high. The atmosphere is much better. In fact, we target if we can move that, we can even observe at terahertz seas. Okay. And of course, we don't have the money yet. We are still trying to source funding for this. Of course, if anyone here, any billionaires or millionaires here are interested, you'll be happy to, if you donate, I think they'll be very happy to put your name on the telescope. Because I think last year, I was telling my boss, I was reading the news in Malaysia, that they found a lot of money in Najib's apartment. Then my boss was saying, hey, when I asked him to donate to the telescope, I have to call it a Najib telescope. I said, please, if you do that, I'll quit the project. Okay? So, but the National Science Foundation in US, they are very experienced with moving things from there to the summit, okay? You're going to do it by land, okay, through on the ice sheet. Okay, it's quite a big process. I think it costs probably a few million USD, okay? And they've shipped big stuff up the mountain before. So, on the summit station, there are actually a lot of scientific research activities going on there, okay? So yeah, hopefully within the next few years, that is the target. And our boss, Paul Ho, is looking for funds right now, trying to get some rich Taiwanese to donate, okay? So yeah, the GLT is all up and running. I already joined some of the EHT observations. And look out for the first EHT results soon. Okay, if you want to find out more information, there is actually a website for EHT, and we also have a Facebook page as well. Of course, please don't be a go and troll the Facebook page, because I think almost every day you can see, can you see the image? I think you all failed or whatever. That's why you're not seeing for so long or whatever. Okay, so yeah, you can check out these websites. And for more on the Greenland Telescope, you can visit this. So Harvard has their own website. ASIAA has our own website. But the ASIAA English a bit not so good. But actually, if you're interested, this YouTube link, right? I actually don't know how to search for this video because I'm a banana. I cannot read Chinese. Okay? So there was actually a Taiwanese documentary about the Greenland Telescope. Okay, but the documentary is in Chinese, English. So if you want to, you can watch. Okay? Are non-Taiwanese. Okay? The journalist who did this documentary actually won an award recently, the Golden Bell Award, which is like some Emmy Awards, Chinese version. Okay? So for any of you, if you like this kind of thing, there are wild Arctic landscapes. So this is a picture you all use for, I saw for your poster. On Sunday, we get a break. We don't work every day. Okay, you can go and we'll go around. This was in summer. Take some pictures of the glaciers. Okay. Yeah, this is in summer. You can go around. This is winter, the same part. Okay, everything is frozen. The whole ocean is frozen. So there are a lot of actually nice places you can visit. If you like to do this kind of thing, yeah, this is winter already. So yeah, the ocean is frozen. Okay, if you like this kind of thing, or if you like to, do wildlife, like to see this kind of wildlife, you see this everywhere on the base. You like to come and eat the food. These pictures were taken from the internet, not mine. My camera skills not so good. I use my camera phone, take not so nice. So these are all from internet, and there's actually musk ox sometimes you see around the base as well. Of course, you want to avoid polar bears. Okay, there are polar bears. When there's polar bears, you have to lock down your room. Wherever you are, you cannot get out of the room. Okay, call it technical delta. Okay, so there are many storm conditions. It's like storm condition alpha, there's beta. Certain ones you cannot leave the base. Storm condition delta is the worst storm condition. Okay, you're stuck in your hotel or you're in the buffet restaurant, whatever, you're stuck there. Okay, but technical delta means it's not a storm, but if there's a polar bear, it's a delta level, okay? Or if there's a terrorist on the side, these two are same, polar bear, terrorist, same kind of danger. Okay? And if they see a polar bear, they try to chase it away, it doesn't go away, they have to shoot it, unfortunately. Okay, so if you like to see, Arctic wildlife, why I'm doing this? It's not real, okay? Actually, ASIAA, we're actually hiring, okay, 2 postdocs to work on the Greenland Telescope, okay? Sorry, nice job. But in academia, we're allowed to do this, right? In other industry, you cannot. So we're advertising for 2 postdoc positions of support scientists to work on the Greenland Telescope. Okay, but anyway, like I said, I work on EHT and GLT mostly for the last 2 years. But I still work on some of my other science, active nuclear, all this. So, if people are interested here, I'm not sure, I'd like to talk to some of the local lecturers and all this. If you are interested in sort of co-supervising students and all this, I'm happy to help. ASIAA, we actually organize summer studentships, okay, for degree or maybe master students also, I think you can actually apply. So this is a 2018 one, but 2019, the call should be coming in a few months, I think. Now they're collecting projects from supervisors. Okay, and they actually pay you some stipend to go and stay there for like 1-2 months. Yeah, in summer. If you're interested, you can give me an email. I can forward to you, when, for some of the students here. Okay, you can work with anybody there. People working on planets, dust, cosmology, whatever. You can work with them. Okay, so for 2 months you work on a project, and then after they actually give you lectures as well, like 2-3 days of lectures on introduction to radio astronomy, or observations and theory and this kind of stuff. Okay, so for whoever is interested, let me know. I can send you an email when the announcement comes out. And we have students from all over the world. And you have optical interferometry now. I mean, some of the VLT telescopes, but not coming close yet to the resolution.
My second question is, what is the chance that in a short time, maybe 1 or 2 years, there will be a confirmed detection of the event horizon with radio astronomy? Is it in many more years to come, or soon to be able to do it?
So that one, I have to be careful. Okay, but like I said, the EHT, the first results will come out soon. Okay, so whether we detected something or not, you see lah. And like I said, you actually won't detect we call it the Event Horizon Telescope, but what we are seeing, like I said, is actually the shadow, which is about 5 times the radius of the event. What we call the photon ring. So, yeah. Any other?
Okay, I got a question. So I'm just curious if there are any space-based efforts to find black holes.
To find black holes as in
Observations.
observations. Okay, so there's another telescope. I don't know if you've got Radio Astron. Okay, it's a Russian satellite radio telescope. And with Radio Astron, actually, you can have very long baselines. So Radio Astron, the orbit, right? Sometimes it will fly. It has an orbit. I mean, it's not circular. So at the furthest point from Earth, the Radio Astron satellite actually is about the same distance as the Earth and the Moon, about 300,000 kilometers. Okay, and Radio Astron is also built for VLBI. So this is what we call space VLBI. You combine telescopes from Earth with the one in space to have very long baselines. Okay, and you have baselines as long as the Earth and the Moon. Okay. Because observed are actually very low frequencies, about 1 to 15 or 20 gigahertz the most, okay? But even at that low frequency, you can already get the angular resolution of Radio Astron is similar to the Event Horizon Telescope, about 20 microarcseconds. Okay, but the problem is radio wavelengths, and when you go to centimeter, 8 gigahertz, the galaxy, there's a lot of scattering, okay? This is what I call interstellar scattering. So because of all the ionized gas, the electron densities, okay, is inhomogeneous, it scatters the radio waves. So at radio waves, you actually cannot see the event horizon because of this scattering. It's so strong, okay? So this is why, another reason why for Sagittarius A star, we have to go to 230 gigahertz, okay? So I'm actually part of the Radio Astron collaboration also, but I didn't actually do much yet, although my name is there in the paper. But they have actually tried to observe M87, at this one, but I think there was no detection, okay, at about the centimeter, at the Earth-Moon kind of baseline. Okay, but when the telescopes were closer together, when they did detect something, but so far no event horizon. But I mean, a lot of the members of the Radio Astron are also members of the Event Horizon Telescope. Yeah, sorry, yeah.
One more question is, let's say you all have confirmed that you have detected event horizon with the EHT, similar to what you have simulated. So what is the next step? Can you even do and find more details of the black hole?
Okay, so
more detailed research on the properties of the event horizon?
Okay, so basically, whether we detect or not, I mean, we want to improve the telescope because I said there's a lot of missing information. The more dishes you have, so actually there are more sites coming up also besides the Greenland Telescope. But what we want to do is not just capture the image, okay? We want to, actually make a movie, okay? Because these things, there's a lot of variability as well. You can actually, if you capture the image over time, if you see a black hole, you can actually see how the stuff falls into the black hole. That's why all these simulations are not just simulating what the image, they are examining what kind of variability we expect to observe over time, over years as well. So it's going to be an ongoing project for many, many years. And, to actually study how matter falls into the black hole and also how these jets are launched. Okay, and try to improve the telescope also in the meantime to get better and better images. Okay. Yeah.
I ask on behalf of Mr. Koay here, I find it interesting. Let's say you have confirmed event horizon exists and you have done a lot of properties. Is it possible that we can actually use it like on space travel, time travel, space-time travel? Or maybe one American documentary producer will produce a movie that you have detected the black hole. It can be used to do research on space-time travel.
Okay, so basically what you want to do also when you produce this is also to confirm some of Einstein's general relativity or this. In terms of time travel, I mean, there's a lot of ideas about using black holes for time travel and all these things. Of course, you have to be able to travel there first, but of course, currently Sagittarius A is 26,000 light years away. It take a long time to reach there. But, a lot of this will probably be more from theoretical work to actually physically, experimentally test whether you can do time travel or the wormholes, for example, all this kind of thing. I guess probably you have to find one that is close enough that you can travel to a black hole and maybe send a probe or somebody there, whoever wants to volunteer. Okay. Yeah, so I think there are some ideas that perhaps black holes, or wormholes you can use to travel through space, through some shortcut or whatever. Right? If you can fold space, travel from one to another Okay, so I think there are a lot of theoretical work done by people like Kipton, has books. I think Stephen Hawking also in his brief history of time also mentioned some of this a little bit.
So can I say that by middle of this year, the announcement is for Sagittarius A star event horizon detection?
No comments here. Cannot comment.
Yeah. But in your talk, you mentioned a lot of Sagittarius A star. Right?
Yeah, so I'll say our main A star and M87.
M87.
Yeah. So if you go to their website, these are the main two we actually believe we can resolve the shadow. The other black holes so far we have not known any other target that we can resolve. Actually, if you want to choose two black holes to observe, if you can only observe two black holes, okay, these are the two you want to observe. Because they are very different. One is, like I said, very quiet. M87 is producing this huge jet, accreting some stuff. So it's very different. You can learn two different kinds, very different kind of physics from these two different objects. And actually, there are people still, because measuring the black hole mass is not a very easy thing. There are many methods where people have come up with how to measure black hole mass, especially when they're far away. We're still looking at, there could be other candidates which we have not identified yet, where the black hole mass is large enough, we can actually detect, the event horizon. And people are still measuring black hole masses, and for a lot of studies. I mean, that's one of the big things astronomers are doing today, measuring black hole masses. Okay.
Aside from measuring the event horizon, what else does the VLT do? I mean the
EHT?
VLI, right? The
VLBI or?
VLBI, yeah.
So VLBI, so there is centimeter wave VLBI, which has been around for a long time. Most of them are studying radio jets. How the jets are, we can't study the launching yet, but they're studying how the jets are accelerated and how they can stay so collimated. How come they can stay so narrow over hundreds of thousands of light years? People think whether sometimes there are winds that are collimating them, or the galaxy itself, the gas in the galaxy itself, is sort of making the jet not expand, but being so narrow. So and VLBI is one of the very useful techniques, because one thing you can measure all these, because the resolution is so good, right? You can measure the location of all these quasars or all these black holes very accurately. And because you can actually reverse it. If you know the position, they've measured the positions of a few thousands of these quasars, okay? You can reverse it. Once you know the accurate position of the quasars, now you can actually measure the location of the telescopes very accurately also, okay? So now they know the positions of all these quasars. They measure the position of the Earth all the time, and we call this geodesy, okay? They can actually measure very accurately the motion of the continents from each other. And even earthquakes, however, they can measure down to millimeter levels. They can measure the Earth's movement, the movement of the Earth's continents and all these things. So people, not only astronomers, are interested in VLBI. VLBI is a very important tool now in geophysics, and where they're using it to measure the movement of the Earth's crust and earthquakes and things. You can see the telescope actually has moved. So, like the Chile earthquake, it has moved by how many millimeters or centimeters. Yeah. And also this VLBI is actually very important to the US Navy as well. They have astronomers who do this. Of course, astronomy has always had a very tight connection with the military. Okay? And they use it. I mean, all our GPS satellites now are based on these VLBI measurements of position of quasars. And actually, I'll talk more about this in tonight's talk, where, our GPS satellites can actually work now because of all these VLBI measurements of these accurate positions of all the quasars. Yeah.
So how about, let's say, a stellar mass black hole in a binary system that is emitting mass from its companion?
Yep.
Can the VLBI resolve that?
Okay, that one is too small to resolve. Even though those are much nearer, especially in our own galaxy, we know a few of these, what we call X-ray binaries. Yes. So they are accreting mass. But in terms of size, they are too small for us to resolve with VLBI. Yeah. I forgot what's the actual size in terms of microarcseconds. We cannot resolve that. So our primary targets are all these supermassive black holes.
Okay, everybody, due to time, so I'm sorry we have to stop the question and answer here. Let us give Dr. Kevin a round of applause. Thank you for his talk. We have from the School of Physics, we want to thank you for giving a talk, and we have a souvenir for you. Can I invite Dr. Chong to help me to pass this souvenir to Dr. Kevin? Yeah.
Okay, thank you. Yeah, I mean, I was still hanging around here, so if people want to talk and chat, yeah.
Okay, so yeah, the talk
Thank
is
you very
over.
much.
You can feel free to talk to Dr. Kevin if you have any extra questions. Thank you.
So at the same time, to